All right, so good afternoon. Section 1.2, I think we're going to split this one into two separate videos today. This one is all about formulas and percents, but I think we'll do a 1.2 part 1 here and focus primarily on formulas, and then I'll do a 1.2 part 2 where we'll focus primarily on percents. So if we're going to focus primarily on formulas, basically our two main objectives are going to be able to read a formula, to be able to understand it and interpret it. So I'll say understand/interpret formulas, understand/interpret a formula, and to actually solve different problems with formulas and solve formulas for different variables. So solve formulas for different variables. Now, before we even get into explaining exactly what I mean when I say formula, I think we've got to kind of answer or ask and answer a really critical question in terms of what actually is this course college algebra about. And so I'm going to pose this. What is algebra? Now, it's sort of a weird word even. I think a lot of classes that you might take, you can kind of, even just by the name itself, it gives you a little bit of information about it, right? So say something like history, right, is literally the story of humanity. Or something like psychology is the study of the human psyche. English class is literally the study of the English language, right? So all of these things, when you take a class like that, it sort of gives you some of the information about what it is you're actually studying. But algebra is sort of this weird word. So when we talk about algebra, what are we really talking about? You could say things like, oh, well, algebra means solving equations and, simplifying expressions and kind of all this stuff that we sort of set the groundwork in from the last video. And all of that's really good. But I don't think it really gets to the heart of what algebra actually is. And I think what algebra, at its core, what it really is it is the mathematics of, the mathematics of relationships of quantities, right? So in math in particular, we care about things that are quantitative a lot. And algebra, we care about how those quantities relate to each other. So a couple of simple examples here. For example, if you went to a restaurant and you ordered a meal, right? So you went to a restaurant and you ordered a meal. That meal is going to come back with a bill, right? And that's some certain amount of money that you're going to have to pay. But then along with that bill, you also were waited on during that meal, right? And so typically, at least in the United States, what you typically do is you pay the waiter or waitress a tip. And that tip is usually determined based on maybe a couple factors. Sometimes you might determine it based on how well they did of a job. But primarily, I would say it's determined on how much the bill actually was, right? So if we have let's say a large bill, that typically means you also have a larger tip, right? And if you have a smaller bill, that would typically mean you have a smaller tip. And so these two quantities are related to each other. If you order more food and your total bill goes up, then the tip that you should pay, at least according to the general standard, the tip that you should pay should also go up. If you only order a few things, then maybe you'll pay a smaller tip, right? So these two quantities relate to each other, right? And we can express that relationship very specifically with what we call a mathematical formula. So for instance, we would write something like the tip, and I'm just going to write this in words for now, but in general we might use variables, but you would say the tip maybe is equal to 20% of the bill. Right, and so this here sort of outlines that specific relationship. Whatever the bill is, take 20% of that, and that's what the tip is going to be. But we can see this in all kinds of places, right? So maybe, for example, we can even think about something like basketball, right? So maybe you are a basketball player and you shoot the basketball, and that goes over some trajectory to hopefully try to land in the basketball hoop. There's things about the way that basketball moves through space that we can understand as a relationship between different quantities, right? So for example, we could talk about how high that basketball is off the ground, right? And its height is going to be related to a bunch of different things. It's going to be related to how long it's been since it's been thrown, right? Right at the beginning of the toss, it's going to be just about as high as the person's hand. But by the end of the toss, hopefully it will be as high as the height of the basketball hoop. So it's going to depend a little bit on how long has passed, so what time. And it's also going to depend a little bit on how fast the person throws it. So for example, if you threw the ball really, really fast, maybe it's going really, really high up. Or if you threw it with very little velocity, then it's not going to make it up as high. And it also depends a little bit on the acceleration due to gravity even. If you play basketball on Earth and you throw the ball at a certain speed, it's only going to make it so high. But if you were to play basketball, say, on the moon, right, that ball would fly a lot further. And so we can create a similar kind of relationship between all of those different variables. In this case in particular, that's going to look like h is equal to v for velocity, as in the speed that they're throwing it, times time, how long it's been since they've thrown it, plus 1/2 times g for the acceleration due to gravity, times t squared. Right, and so this here is a formula that represents the relationship between all of those different quantities: the height of the basketball, the speed at which it was thrown, the time since it's been thrown, and the acceleration due to gravity. Right, so we put all those together, and we have a way to very specifically, very explicitly represent the relationship between those types of quantities. And this is what we call a formula. So a little bit more specifically, we can say that a formula is an equation. So we're setting things equal to each other, but a formula is an equation that describes some relationship between quantities. So it describes a relationship between quantities, right? So it really does get to the core of what algebra is all about, right? And we saw a couple of examples of this. We saw a couple of examples of this already, right? The height of the basketball was related to time, for instance, right? Or the tip was related to the bill. Right, and so we've got different examples of this and how this works already, and there's tons of different ways that you can use this all across essentially everything that you might do out in the real world. And so that's part of what makes algebra so interesting and so valuable. One thing that we also care about, though, is being able to sort of manipulate those formulas and work with those formulas and solve problems with those formulas, so that we can find out different pieces of information. for example, let's say that a waitress earned, $20 for a tip. Right? If we assumed that the person doing the tipping was doing it at a rate of 20%, so assuming that we had this formula of the tip equal to 0.2, right, 20%, which we'll touch on in the next piece of this, the percent piece. But assuming that t was equal to 0.2 times the value of the bill, we can find what the bill is. So what was the bill? Right, and so we have the ability to solve something like this. Now, we could sit here at this point and we could start to plug in some of the information that we know, right? For example, we know what the value of the tip is. It's $20, right? And so we could plug that in and then treat this kind of like an equation that we would have solved in the previous section. And that's totally fine, but there's a better way to do it, which is to actually just solve for the variable that we're looking for first, and then plug in all of the information to do the calculations later. Now, it doesn't make a ton of a difference on a problem like this as far as which method is going to be easier. They're pretty much the same. But when you start to get to more difficult problems that have a whole bunch of steps and a whole bunch of compounding calculations, it's going to be best when you can to try to do this. So what we'll do, for example, is first solve just for b. Now, when I say that, I really mean solve for b in the same way that we solved for x in the previous video. We can do all of the same things, even though there are variables here. We can do all of the same things that we did with the numbers in the last episode, solving for b in the sense of getting b all by itself, isolating b, so that we have a formula specifically for b, a formula explicitly for b. Right, and so what would that look like? Well, we would say something like, all right, we know t is equal to 0.2 times b. We've got this multiplication here, right? We've got this multiplication here. And in order to get b by itself, we know from the last video that we have to undo whatever that operation is. So if it's being multiplied by 0.2, if we want to undo that to get rid of it, to get b by itself, we will divide it by 0.2. And of course, because this is an equation, we're going to keep that on both sides. We're going to perform that action on both sides, I should say. And so now we would have b, and I'm just going to flip the order of these so we can write this more explicitly, but we have b is equal to t, divided by 0.2. Right, and so now we have this formula for b, right? It is an explicit formula for b that tells us whatever value we put in for t, so whatever that tip is, we can find the value of the bill if we just divide it by 0.2. Okay? So we can solve for b to get an explicit formula for b, and that's our step one. And then from there, we can evaluate our new formula, for t equal to 20, or whatever the specific one is in your case. But in our case, it's 20. So we'll evaluate for t equal to 20. And of course, we know how to evaluate expressions now based on what we did in the last video. So we will take 20 and we will plug it in for t. Right, and so now we have b, the bill, is equal to 20 divided by 0.2. Okay, and all that's left for us to do now is to do the actual division here. And so 20 divided by 0.2 is equal to 100. Okay, and so that means that the bill was $100. So therefore, that's what these three little dots represent. Therefore, the bill is $100. right? And that's not so bad. There's all kinds of different ways that we can do this though. And this skill is going to be really, really important for a lot of what we do in an algebra class. Okay, so let's consider one more example. Let's say that the perimeter of a rectangle, so the length of the outside edge, the perimeter of a rectangle is given in terms of length and width. When we just say in terms, it means that we're going to have a formula that is explicitly for perimeter and is going to depend on the variables of length and width. So these are the three quantities that are related here. The perimeter quantity is related to length and width. It depends on how long and how wide the rectangle is. And so let's say that the perimeter of this rectangle is given in terms of length and width by the formula P for perimeter equal to 2 times W for width plus 2 times length, 2 times L for length, right? And this really makes sense because we know what a rectangle looks like, right? A rectangle is going to look something like this, right? Where we have two sides that are the long side, we call those the length. Two sides that are the shorter side, we call that the width, right? And so the length of the whole way around this is going to be, well, we pass L twice and we pass W twice, so 2W plus 2L. So that really does make sense. And what we might want to do here is maybe we, for example, maybe we have a certain amount of fence that we want to fence around an area with, right? We've got our backyard, we want to fence around an area, and we know we have to make it, at least 20 feet wide. We might wonder, well, how long could we make it then, right? So we might want to be able to find the length given those parameters. Okay, one thing that we can do is we could rewrite this formula to solve for a formula explicitly for length. And so if we can solve for L, then no matter what that width is that we know we want, we can figure out what length we can make with the perimeter of fencing that we have. So we can do sort of the same thing here as before. We will solve for L. And again, when we say solve for L, yes, in this case, we're using things like P and variables like W instead of just purely numbers, but all of the actual processes and rules for this will follow the same sorts of patterns. So for example, our goal here is still to isolate this L. We still want to get L by itself so that we can solve explicitly for L. And so we've got to do all of the same sorts of actions as we did in the previous video to undo all of the operations on L and isolate it and get it by itself, right? So for example, we've got this plus 2W over here. If we want to get rid of that to get L by itself, well, we're going to have to subtract 2W from both sides, right? And of course, we've got to do it from both sides in order to maintain equality, but we've got to subtract 2W. And once we do that, on the left-hand side, we'll have P minus 2W, right? We can't actually combine these because they are not like terms, but we've got P minus 2W and then 2L left on the right. We can continue this one step further. If we divide both sides by 2, right? 2 is being multiplied, so we'll do the opposite action, we'll divide. And once we do that, then we will be able to get L by itself, right? Because the 2 here in the numerator and the 2 here in the denominator will cancel each other out, right? And so that's going to leave us with L equal to P minus 2W divided by 2. We could do a little bit of simplification on this if we want to rewrite this a little bit. Perhaps we would say distribute this division, right? So we're dividing by each of the terms. We can divide the 2 by the p, and we can divide the 2 by the 2w. Now the reason we might want to do that is because 2 over 2 is just 1, and so we could rewrite this then as w. But this now gives us a formula explicitly for L, explicitly for the length. So if we know we have our fixed perimeter of fencing, right, and we know what width we want to make it, then we can automatically tell by plugging into this formula what length we would need. Obviously, there's going to be a lot of different variations of this. There's so many formulas that you can use in so many different fields and so many different topics outside in the real world. But this process that we kind of started working on in the last video, it's going to apply the same way for formulas as well. The only difference here is that now we're going to be working with variables so that we have a way to express relationships between different quantities, right? And so we can kind of wrap up with that, remembering that algebra is really all about how we relate different quantities together, and working with these formulas is going to be an explicit way to help us represent those relationships in a mathematical and quantitative way. All right. I hope you found this video helpful. Let me know if you do have any questions. I will follow this up pretty soon with a part 2, all about percents. But otherwise, thanks for watching, and I hope you have a great rest of your day.